Welcome to this NEC code class. This is question number 8 from book number 1, based on the 2020 NEC by electricaltime.com. The transformer supplying power to an office building is rated 75 kVA, and the secondary side is 208 Y/120 volts. It's going to be three-phase and has an impedance of 2%. You take out your sticker and are going to field mark the available fault current and today's date on the sticker. For the purpose of keeping this as simple as possible, assume an infinite current on the primary side and ignore any additional impedance from your service entrance conductors since they are only 15 feet long. Calculate the available fault current with a 10% tolerance of the transformer's rated impedance. Hint, take the impedance and adjust it by 10% so that your available fault current becomes larger. Even though the transformer has a marked impedance of 2%, it's practical to assume that the impedance will vary plus or minus 10% during the life of the transformer. When it comes to this calculation, it's better, in my opinion, to document a larger available fault current to help ensure that you select the proper equipment. What is the available fault current? And we got a couple of choices here. Just want to take 30 seconds to let you know what we do here at electricaltime.com. We do online electrical classes from the comfort of your home. And then we also have this free service. So if you click on the subscribe for free NEC questions, Monday through Friday, you'll get an NEC code question and an answer sent to your email. All right, so back to our video. And I know initially, any of them, could be the right answer. We just don't know. We're going to have to do the calculations. So let's take a look at our textbook and see what we got here. First question we're going to ask ourselves is, what article are we talking about? And that's going to be Article 110, Requirements for Electrical Installations. And that's within Chapter 1, General. And when we go to an article, we're going to look at the parts, and we see Part 1, and that's called General. Then we see 110.24, and that's Available Fault Current. And then we have 110.24a, and that's called field markings. So let's go into our code book and let's take a look at 110.24a, and that's titled field markings. If you don't have your code book, just go back to our website, electricaltime.com. Click on the picture of the code book, go buy your code book, go buy your tabs. All right, so here goes. Again, this is 110.24a, field marking. Service equipment at other than dwelling units shall be legibly marked in the field with the available fault current. The field markings shall include the date the fault current calculation was performed and be of sufficient durability to withstand the environment involved. The calculation shall be documented and made available to those authorized to design, install, inspect, maintain, and operate the system. We also have a B in there, and it's called modification. So make sure you check those out in your code book. All right, so let's continue and see what we got in our textbook here. So here's step 1. Here's what you do. You call the electrical inspector and make believe you're too busy to do this simple calculation so that if he or she gives you a wrong number, you can lay it back on him or her. Just kidding. You need to know how to calculate this and need to show it to the electrical inspector when asked. All right, back to me here for a second. All right, so what's going to happen is we're going to go through a calculation here. It's going to look a little complicated, but it's not really complicated. Once you've done this a couple of times, it's actually pretty easy. All right, so make sure you have your calculator ready and maybe get some aspirins and maybe just listen to the rest of the video. And then, you can go ahead and practice it later on. All right, so back to the video. All right, so now step 2. I'm going to memorize this formula. Also, don't forget, we're talking about three-phase, and we're going to use 1.732. And you're going to say, hey, Steve, where did you get this 1.732 from? Well, that's real simple. If we take the square root of 3, that's equal to 1.732. And that's where that number comes from. All right, so here's the formula. Got AFC, and that's going to stand for available fault current. And we've got KVA, and that's from the transformer. It's 1,000, and we're going to multiply KVA by 1,000. Then we're going to take the voltage on the secondary, multiply that by 1.732 because it's three-phase. Then we're going to take the impedance that we were given, and then we're going to multiply it by something that I'm going to call the net tolerance. And that net tolerance, remember I said in the question that we're going to have a net tolerance of 10%, and we want that available fault current to be larger. And that's where that came from. All right, so let's continue. So we got available fault current, AFC, is equal to 75 kVA times 1,000. And over here, we've got the voltage times 1.732. Over here, we've got the impedance of 0.02, and we got this net tolerance of 0.90. All right, so when I said, this 10%, net tolerance, and we want to make the available fault current worse. So what we do is we multiply that by 0.90. All right, and you can play around with the numbers, and you could see that by making it 0.90, we're making this worse, because when the impedance becomes lower, the available fault current is going to get larger. All right, so here goes. So available fault current is equal to 75,000 VA, and now we're going to divide that by 360.256, and we got that number by multiplying 208 volts times 1.732, and then we're going to multiply that by 0.018, and we got that by the 2% impedance times the 0.90, and that gave us our 0.018. So now let's carry this down to the next line. Available fault current, AFC, is equal to 75,000 VA divided by 6.484608. And when we do that calculation, available fault current is 11,566 amps. So let's continue here. I got some other things in our textbook that I'm going to read to you. When I took the impedance of 2%, which is also expressed as a decimal of 0.02, I reduced the impedance by 10% to effectively account for the 10% tolerance and got 0.018. Also, for our new electrical students, when the transformer or anything is referenced by kVA, the letter K means kilo, which is equal to 1,000. So 75 kVA is equal to 75,000 VA. Okay, I got some more stuff in here. Okay, let's see what I wrote. Note, I named this formula AFC because it made more sense to me versus other abbreviations that I have seen. Also, and just for clarification, I took the impedance of 2%. And let's stop here for a second. We got this word impedance. And, what does it mean, from our perspective? And back to me. All right, so I'm sure we've all heard of the word resistance. And now we hear this word impedance. And what is it? So resistance is associated with direct current, and impedance is associated with alternating current. So without getting too crazy on electrical theory and everything else, so when you hear impedance, just think about, resistance. And I think that's going to help you to understand, what that word means. It's different, but it's the same. All right, so hopefully that helps. Okay, back to the question. I took the impedance of 2% and multiplied it by 90% to reflect a 10% tolerance, which effectively reduces the impedance, which increases the available fault current. I also told you to ignore the service entrance conductors, which would have introduced additional impedance, which would have effectively decreased the available fault current. That calculation is a bit more complicated, and I just wanted you to get your brain focused on the initial available fault current, the AFC calculation. When you initially do this calculation on an app from your cell phone, which we'll do a little bit later in the video. I'm actually going to open up an app, and we're going to run through this calculation so you can, go check out the app, which I think is pretty cool. And when you do this on your cell phone or computer, don't enter the service entrance conductors or the feeders from the secondary side of the transformer, and write down the AFC it gives you. Then go back and add the conductors and see that the AFC, the available fault current, is now lower. And that's because those service entrance conductors or those feeders, they've absorbed some of that available fault current. Depending on the size, material, and length of those conductors, it can have a significant effect on the available fault current, AFC. All right, and I still have some more stuff in my textbook. Wow. This question took me a whole day to write, and I rewrote it a couple of times, and maybe I went a little bit overboard, but that's okay, because I want you to understand some really important concepts. So let's make sure that whatever you connect your power to, that your equipment can handle the available fault current, which it can deliver, which we call on the receiving side the short circuit current rating, and we also call that SCCR. Let's say that the available fault current is 12,000 amps and your equipment can only handle 10,000 amps of SCCR. You could be putting someone's life in danger and or burn down the building. So the answer to this question is going to be 11,566 amps as the available fault current. All right, so I promised you I was going to show you another way to think about this, and here it goes. So I'm sure we're all familiar with this, and this is the pi formula. So what we're going to do first is we're going to calculate the full load amps for the transformer. And let's do that. And that's something you got to know anyway when you're sizing conductors for the transformers. So let's going to solve for I. So I is going to equal to P divided by E. I is going to equal to 75,000 VA, and that's the same as 75 kVA times 1,000. And we're going to divide that by the voltage, and that's going to be 208 volts times 1.732. And let's see what we come out with. So I is equal to 75,000 VA divided by 360.256. And I'm going to grab my calculator to make sure that that is the correct number. So if I take 208 times 1.732, that's going to equal 360.256. All right, so let's continue with this calculation. So my amps now on my secondary side are going to be 75,000 divided by 360.256, and the amps are going to be 208.19 amps, and that's going to be the full load amps on that transformer. So, okay, so what do we do now, Steve, that we got this, 208.19 amps? And don't confuse it with the 208 volts. It just happens to be that, they just came out to be very similar numbers. All right, so here's what you do. We're going to take that impedance. And remember we had that 10% tolerance? So what we're going to do is we're going to divide that by the impedance of 2%, which is 0.02. And we are going to multiply that by the 0.90. And that was for the net tolerance of the 10% to make the available fault current higher. We wanted to make it worse. All right, we want to have more available fault current. All right, so when we do this math here, this comes out to 0.018. So let me just pull that out on my calculator just to double check. So I got 0.02 times 0.90, and that is 0.018. So now, if I take the 208.19 and I divide it by this 0.018, and I'll write this down over here. So I'm going to have 208.19 divided by 0.018, and that is going to give me, and I'm going to pull up my calculator, 208.19 divided by 0.018, and that is equal to 11,566 amps. And that's the same number that we got when we did our formula here. The same exact number. Now I'm going to show you something pretty cool. I'm going to open up an app that I found that I think is a great app. And there's a lot of apps out there. And here's one of them that I think is actually a pretty good app. It's called the Eaton Busman app. And you can download this, I guess, on your Android or your Apple phone. I have it on my tablet. And let's go through the calculations here and see what we get. So we're going to select three-phase. And now I'm going to select Add to My System. And I'm going to add a transformer to the system. And I have two choices. Yes, I have a known primary fault current. No, assume infinite current on the primary. So I'm going to select no, assume infinite current on the primary. So it's asking me for my kVA, and I am going to enter 75, because remember, it's 75 kVA. It's asking me for my voltage on the secondary, and that's going to be 208. And it's asking me for my impedance, and my impedance is going to be 2%. Now, it's also asking me something here. There's a check mark. It's checked at minus 10% max fault. So you can do 0, which would be no change, or you can say plus 10%, which would give you the minimum fault. But what I like to do is I like to put minus 10%, and that gives me my 10% tolerance so that my available fault current gets larger. I want to make it worse so that I make sure that I get the right equipment. And now I'm going to click Add to System. Now it's asking me if I'd like to add motor contribution to this voltage, yes or no. And back to me here for a second. All right, so when we have a motor and the motor's being powered up, it's turning. So what happens when that voltage, when that current stops? Does that motor just stop? No, it keeps on turning for a little bit. Now that motor now starts to act like a generator, and it's sending power back to where it came from. So if I got my transformer over here, supplying the power, let's say, to the switchgear, and now I've got this motor over here, it's still turning even though the power's turned off. It's actually contributing, something back. So you've got, two sources of power which actually can elevate the available fault current. All right, and that's what that means. All right, let's go back to our demonstration here. Again, also for Eaton, I don't work for Eaton, so I don't make anything off of this, but I think it's such a cool app, and that's why I wanted to show it to you. So I'm going to select no on this, and now what it does, it actually creates what you can print out this as a sticker and put it on the equipment, and and there you go. So this is a really cool app. And again, there's other apps out there, but that's the one that I was introduced to, and that's the one that I'm used to at this point. All right, so if we look here, we can see after all of these calculations, we can see that we've got 75 kVA. The voltage on the secondary was 208. The impedance, which is represented by the letter Z, is 2%, and we have a tolerance for Z, which is minus 10%. And then what it gives us here at the fault of X1, it tells us that it's 11,567 amps. I know it's a little hard to read, but that's what it's given us. It's giving us 11,567 amps. All right, and remember I told you about, doing the service entrance conductors or the feeders at a later date. So, let's do that here as well. So I'm going to go and now click Add to My System. Okay, so now that we calculated the available fault current, both ways using those two different variations of those formulas, let's check out this really cool app that I downloaded on my iPad. I also downloaded this on my Android phone, and it's called the Eaton Busman series. I don't work for Eaton. I don't make any money by advertising anything for them. I just think that it's a really cool app, and there's other apps out there, but this is the one that I started using and I got used to it, and it's actually a pretty good app, and it actually prints out a label for you that you can stick on to that equipment to make that inspector happy. All right, so let's run through some calculations here and see what we get. All right, so I'm going to click Add to my system. I'm going to add transformer to the system, and I have two choices now. It says, do you have a known primary fault current value? Yes or no? So I'm going to select no. So I'm assuming that we have something called an infinite current on the primary. And now it's going to ask me for the kVA of the transformer. And that kVA is going to be 75. So I'll put 75 in there. And now it's going to ask me for the voltage on the secondary side. And that voltage on the secondary side was 208 volts. It's also asking me for the impedance. And the impedance in our example was 2%. Now also, let's take a look here. We got some choices on the bottom for tolerance. So by default, they're picking minus 10%, which is going to give us the maximum fault. And that was the same thing when we had in our example, where I took the 2% and I multiplied it by 0.90. And that basically that increased the available fault current. Now, you also have a choice of selecting no change, or you can actually, pick plus 10%, which would minimize, which actually would make that available fault current smaller. But the way that I do this, I always take worst case scenario when I can, and I'd rather have the worst case scenario to make sure that that equipment that's being installed, that it can handle, that available fault current if it should ever happen. So let's click now Add to System. And now it's asking me if I have a motor contribution. All right, so come back to me. I'm going to try to explain that a little bit here. Okay, so, when we have a motor, so that motor's turning, right? And what happens when we turn that power off? Does that motor stop turning right away? No. So the motor's turning, the power turns off, and now that motor slowly starts to slow down and eventually stop. So while it's still turning, that motor can act as a generator and, supply power back, to that, that switchboard or that switch gear. And remember what's attached to that switchboard or switch gear or to that panel board? We got our transformer out here, and that's supplying power that has that available fault current. So if I got the transformer, giving me some available fault current here, possibly, and I got this motor that's still turning even after the power's been turned off, I've got a contribution going back to that switchboard, to that switch gear, to that panel board. And that's what that means. So if you really got to understand the calculations here, and if you're not sure, you can always ask an engineer. You can ask your electrical inspector for guidance on that. All right, let's get back here. So we're going to select no. I do not want to add a motor contribution, but you might have to, depending on the situation. All right, so I'm going to select no. And let's see what this has given us at this time. So it's telling us that, it's 75 kVA, 208 volts. We see the Z, which is the impedance as a percentage, and that's 2. And then it's giving us the percentage ZTOL, and that's going to be the tolerance, and that's going to be minus 10%, which is going to increase that available fault current. And what do we have here? It tells us that the available fault current, per this calculation, per the app, is 11,567 amps. And that is the same number that we had. Well, basically, it's off by 1, but, who cares? But it's the same number that we just calculated by hand. And how cool is that? All right, so what we're going to do now is we're going to add the conductors, to this system. And we're going to see how adding the conductors changes the available fault current. All right, so now I'm going to click Add to my system again. And now I'm going to add conductor run to system. And it's asking me for the length of the run. All right, I'm going to go pick a number. I'm going to pick 200 feet. Let me type that in here. Okay, I got 200 feet. And it's asking me conductors per phase. So let's say I'm going to have 2 conductors per phase. All right, just for this example. And it's going to ask me for the conductor size. And let's say that we are going to pick 4 aught. Right? I'm just going to pick 4 aught. I'm not doing any calculations here. We're not doing any calculations for Article 450 for transformers. Right? We're just picking some numbers to see what effect this is going to have on the available fault current. And let's say I'm going to pick my conductor material. Let's say that's going to be aluminum. And it's asking me for the conductor type, and that's going to be 3 single conductors. It's also asking me for my conduit type, and let's say that I'm going to put this into a non-magnetic conduit. Let's say I'm going underground. I'm going to be using PVC. Now that we've added the conductor run, and again, I'll go over it again. We said, hey, we just picked the number, 200 feet. That's going to be our run from the transformer to, let's say that panel board or that switch gear that we have out there somewhere. And that we're going to run 2 conductors per phase. And I just happened to pick 4 aught aluminum. And we're going to have 3 single conductors as the conductor type versus a 3-conductor cable. And the conduit type is going to be non-magnetic. All right, so let's see what happens to the available fault current now. So I'm going to click Add to System, and then I see this diagram again. And again, this is something you can print if you've got the right printer. Print it and make sure you stick it on that equipment and make sure that it's going to be, durable for the environment. That's not going to fade away, like in 6 months or less. All right, so we can still see that on transformer T1, that our available fault current is still 11,567. But let's take a look now. Let's look at the conductor run. So the length of the conductor was 200 feet. The size of the conductor is 4 aught. I got 2 conductors per phase. We have 3 single conductors. The conduit type is non-magnetic. So, that could be your PVC. And the wire type is going to be aluminum up to 600 volts. Now let's look at the fault at X2. X2, the available fault current, it dropped down to 6,213. And again, this is the diagram here. And you can print this, and it has an option here to create a label. So, if you're in the field and you have to do this calculation, this is a great app. Again, I don't work for Eaton. I don't make any money advertising, their app. They're just a great company. And if you ever get a chance to watch any of the videos by Eaton, there's a fellow by the name of Thomas Dimitrovich. He's a really cool guy, and he goes into, a lot of the higher level theory things that we really need to think about as licensed electricians and electrical inspectors. All right, so back to me here for a second. All right, so we went over a lot of things in this video. We did the calculation, we did the formula that I called AFC. Then we used the pi formula, and we saw that we got to the same number. And then we also used the app by Eaton. And again, there's other apps out there, but I just happen to like that app. All right, so I hope you enjoyed this video. I know it's a long one, but feel free to play this video over and over again until you start to really understand what's happening here. And then you'll see when you're in the field, when you have to do this calculation, that you will be that expert. And also, don't forget, in 110.24a, it talks about that we need to do this available fault current calculation for other than dwelling units. So, if it's a house, you're not going to do this calculation. But if it's other than a dwelling unit, you must do that calculation. And you got to have that sticker on that service equipment. All right, hope you enjoyed this video, and we'll see you on the next one.